Okay, I'm going to be
talking about
talking about
a couple
a couple
stars
stars
today.
today.
First
This
one
first one
is
is clear at the
the
opposite end of the
scale
scale from what we
heard
just
about,
heard about with the
very
very
luminous,
luminous, very
gigantic,
gigantic,
long
long
period
period
Myra
Myra
variables.
variables.
I'll
I'll
be
be talking
talking about what
about
turns
what
out to
turns
be
out to
a
be
delta
a delta
Scuti
Scuti
variable.
variable. Oops, is to go the other way.
Let's start this
Let's start
tale
this
with
tale with
review, actually,
review
a couple
actually
of slides that
slides that
I've used
I've used
before
before in
talks here.
talks here at the
So,
AAP. So this
this
unusual
unusual
telescope
telescope
system
system
is
is
the
the
Kelt
Kelt
telescope,
telescope, which
which
stands
stands
for
for
the
the
1
degree
extremely
extremely
little
little
telescope,
telescope,
which
which
I
I
think
always
is
think is
it's
it's
interesting in
interesting
and of
in and of
itself with
itself
the
with
age
the
of
age of
extremely
extremely
large
large
telescopes,
telescopes,
super duper
super
large
duper large
telescopes,
telescopes, and
30-meter
30-meter
telescopes, and
telescopes,
whatever.
whatever.
Um,
Um,
the Kelt
Kelt
survey
survey
telescope
telescope
is
is
really
really
just
just a
a
CCD
CCD detector
detector with a
80
80 millimeter
focal
focal
length,
length
high
high
quality camera.
quality camera lens attached to it.
Gives
It
the
gives
field
a
of
field of
view
view
of
of about 26 degrees on a
side.
side.
The plate
The plate scale
pretty
is pretty
coarse
coarse
at
at
23
23
seconds
seconds
per
per
pixel.
pixel.
So
So
anything
anything
within
within
about
about
an arc
an
minute or
arc minute
so
or
of
so
your
of your
target
target
object,
object, there's a
there's a possibility
possibility
it
that
can be
it can be
blended
blended with
with another
another
nearby
nearby
object,
object, a star. Uh,
kind of
Kind of
the
the bane of the project is
the undiscovered
the undiscovered eclipsing binaries that lurk out there, and
much fainter
much
than
fainter
the
than
target
the
object,
target objects, but
close
close
enough
enough
that
that if they're
a
varying
couple
by a
tenths of a
couple
magnitude,
tenths of a
that
magnitude,
makes
that
the
makes the star look like it's
got a nice little
got a
wiggle
nice
in
little
there
wiggle in it every
once
once in a while.
in a while.
So
Some
some of the false positives occur that way. And because
have
of this, we
the
have the
follow-up
Kelt
team.
follow-up
The
team.
object I'm going to be
The object I'm
talking
going to
about
be talking
today
about today
is
is
the
result of a detection originally in the Kelt survey, as I'll mention, but it was followed up by one of the observers
in that
in
follow-up
that follow-up team in the summer of 2014. Giorgio Corfini, one of the Italian observers that's part of the project, noted in his
observing
observing of a
candidate
candidate star
in
in
field
field 11
that
that there was a
relatively
relatively
bright,
bright,
about
about 12
12
magnitude variable star in that field as well.
and
And he was diligent and looked it up in the VSX and found no listing, and searched around other sources and found this had not been identified as a variable star, and made that report to the Kelt follow-up network. Um, and there's quite a process involved in that where the candidate objects are selected, see if they meet criteria that they can possibly be extrasolar planet transit candidate, and this object had been noted as displaying some type of variability, but the algorithms that are used to search for possible transits were just not able to adequately fit a predictable ephemeris to these events that come up with anything that looked like a transit. Now the survey, and I think ESO is
already
already starting to be part of this. They've found lots of undiscovered variable stars, eclipsing binaries, and different pulsating stars. So there's lots of stuff I think that will provide some interesting targets into the future. Anyway, this star originally had been given this identifier. It means it's a candidate field 11, and then assigned that sequence number. So, but it had failed the initial selection criteria. But when Giorgio had made this announcement, it caused them to look it up again, and with the depth that he had reported, which was just for a partial transit event, which turned out not to be a transit, but we'll get into that in just a minute. With that information, there was renewed interest, and this is a kind of unusual level of confusion for this project, because mainly things are, they make the cut or they don't, and once they're eliminated, it's pretty much forever. And then this report comes in and it looks like, oh, maybe there's a possibility for this once again. And so it was on the list for a grand total of about a couple weeks where it was actually active. But in that time, they adjusted the window for the transit event, I think 3 different times, depending on when observations came in, and it looked kind of weird. And so I'll show you what happened. The result was that it never actually got removed from the list, and so it was still a low priority object that got some observations. In August of 2014, Eric Jensen at Swarthmore and João Gregorio in Portugal, and then myself at West Mountain had all taken a set of observations, and kind of late in getting some of them reported because all of us are busy, but it took 10 days to actually get the reports. They all come in about the same time. And as a result, especially my observations were the last, I think, a day that came in of that set. And I'd commented in my report that this really looks like a multi-periodic, delta Scooby variable, fairly low amplitude from what I was seeing. And thought it would be left at that, and this was a star that was eliminated from the list forever. But it got assigned this priority 1, which is the lowest priority, but it stuck around for a little bit longer. So, unfortunately, the event that happened next was one that wasn't foreseen. That is, Giorgio passed away in December, kind of unexpectedly of a rapid illness. And so this star it just stayed on the list and was known as Giorgio's object of interest. And so it was there, and here are those initial observations. These are Eric Jensen's, and he thought he was seeing a much deeper V-shaped eclipse event, and had noted that in his report. But questioned the quality of the night over here. Comparison star counts had dropped, and we wondered if something weird had happened. That little dip or step, as he called it. But it was interesting to note here too that the transit interval is about an hour and a half. Dow's observations, and the transit interval had been widened out to several hours, and he had observed with the original window, and so he got a much shorter picture. But he said, I have a sawtooth-shaped light curve. I plotted mine on a little different scale. Like I said, these all came in kind of together. But I looked at this, 2 humps, and that looks like a low amplitude delta Scooby star to me, and wrote that in. And like I said, I thought that this was eliminated from the Kelt Transit list. It was still there a year later, in September, on a night when I really had nothing I could do. I wanted to do a Kelt target, and there was just nothing going on available that night. I thought, okay, I'll look at this star. I think I remember doing this a year before, and so I observed it in 3 color filters this time, just to see what I would get. And lo and behold, I got in the B filter, fairly sizable amplitude, and was that 6/7 hundredths of a magnitude. So yeah, it's pretty good. It obviously is different frequencies meeting against each other and changing the shape of the light curve. My B observations on the same night. I also noted this. These observations, this is with the new latest window, and I think the transit fitting algorithm was picking these places where you get 2 relatively high maxima and a lower one in the middle with 2 minima, and on average, looks like it could work, and especially with the errors that we look at with the Kelt survey, it was thought that that could fit. But it doesn't look like that when you get an actual light curve plot in it. And then my eye filter observations are lower amplitude yet, and but otherwise show the variability, and pretty much the same pattern as we see in the other filters. Okay, I wanted to just
go over real
go over
quick
real
here.
quick here
A
a couple pictures of our observatory at West Mountain, where we took the rest of the data used in this presentation. Looking off toward the west, it looks like the beginning of another beautiful night with the sun setting back behind us. And pardon? Okay, here's our field of view. It's about 20 arc minutes on the side, centered on our star, which is Tycho 2168-132-1. And some of the comparison stars are stars of interest. I actually been observing that more than just one shot in a night, but doing it for 4 nights in about a month. I did notice that there are, I think, 3 other stars in this field look like they have eclipses happening in 1 to 2 week periods. And so I'm going to target this and follow up and see if I can get particulars on those suspected binaries right now as well. I used VFOT to do the first runs on our data reduction for all 4 nights in 2015. After I made my initial 2015 report in September, the star was dropped completely from the Kelt Transit Finder, and I had talked with the project leader, Josh Pepper, and got the go-ahead and observe this as a project so we could write up the discovery of this. And yeah, process several nights. Now you see it. Some of the light curves really very different at different times with the different frequencies adding together. Anyway, we collected all the data and determined the times of maximum light in each of the filters, and we're able to start then an analysis of the periodicity that we observed. We did have a couple of our times from the previous year, and then some of the nights where we didn't observe in the R filter. We were just doing BV and I. We went through after we used to determine the times of maximum light. We did 2 different fitting routines in Peronso, the software package, to get the times, and then Period 04 and some of the routines then in Peronso to check it. And it was interesting, and this really isn't in my wheelhouse to have non-radio pulsators, multi-periodic, and you know, as complicated as this one's turning out to be. I'm used to working on the high amplitude delta Scuti stars that are either well-defined periods that fit within the accepted period ratio, or one really period in the light curve. And we found in this, in the BV, R, and I filters, all 4, these 3 frequencies were easy to find and popped right out. In the other filters, though, the B filter, there were 3 different frequencies and 3, kind of the same range, but very, very different in the shapes of the light curves, I guess, at the lower amplitudes. R and I had 2 more frequencies that we were judging were above the minimum detection level that we had judged by the signal noise. And so still this shows the amount of this is a work in progress, that not really quite sure what this all means, but figured out, not surprisingly, around the primary we do get in that short of time, we do get a flat O-C. But one thing that has kind of bothered me is how much spread there is in the size of the O-Cs within just a few days. It shows that the light curve itself is, very much changes shape from cycle to cycle, and it's hard to get the contribution to the primary period alone, I guess, is what I'm trying to say. These are the curve fits to B, V, R, and I for the 4 nights in 2015. So we are with the frequency we detected reasonably well reproducing the observed light curves in all 4 filters. The B and V light curves, and difference those, you got these really weird E minus V temperature curves of the star, and probably the most reassuring thing I find about that is that B minus V is changing, and that it's in about the range on average that the Tycho catalog reports E minus V as being. Other than that, I'm still a little bit leery about our colors on this. We looked at data from the Y satellite because the average color is about 0.5, and for a Delta Scuti star, even one that's on the red edge of the instability strip, it's too red of a color. And so I thought, oh, we'll look at the frames from Y's and really see it. That little blue circle around there is actually the point for our star. I can zoom on it a little bit, bring it up to the scale of our image at the beginning from the 0.9 meter. And there you can see that there's I see a lot of material. This is in the constellation of Cygnus, so there's very distinct possibility that there's a lot of influence from interstellar reddening and making the colors look different than what the intrinsic colors would be. In addition, we've looked at the spectral energy distribution by plotting here in the bottom black curve. I almost put it into red on this picture from my angle anyway. We have our B and V points, the Sloan survey, JH and K magnitudes, and then the two WISE satellite infrared, far-infrared observations that we could get. We couldn't get the W3 and W4 filters because the object was just too faint from the satellite in those wavelengths. What we've done here is taken the Planck curve is fit from an F2 type star. That this one we reddened the curve to by 0.2 magnitude. This we left it at the red edge of the instability strip, and this at the blue edge of the instability strip, and just showing that we kind of are fitting that spectral energy distribution to a star of a given spectral type at different levels of reddening, and that we are reddened beyond the red edge of the instability strip. So kind of think that we can at least get an estimate of the reddening from this. And so that's my preliminary conclusions so far about this star, that we have a multi-periodic variable star. Its period primary period is about 1 hour and 46 minutes. The frequencies, first 3 frequencies, do show up in all 4 colors. It's likely a low amplitude Delta Scuti star. Its reddening is greater than 0.2 magnitudes. And these properties are consistent with a Delta Scuti variable in or the star in general in the lower part of the classic instability strip. And I actually wanted to show one other thing real quick. It's a different project, but it's really fun, and it's kind of has some bearing on the talk we just listened to, because these are observations of a white dwarf that it's a star that's going to come through the evolutionary sequence that we just talked about, and obviously had something like planets orbiting around it, maybe an Earth that didn't. But I don't know if it didn't look like it maybe partially escaped, because this is the timing on this. It's going to orbit about every 5 hours, so it's been moved in really, really close to the host star. And evidence is from the transits of this white dwarf that this is also an object that's kind of breaking apart and disintegrating. From other ones I've looked at, data that's in the literature, I haven't seen the two peaked ones like I picked up. A lot of observations show more of a tail here on the trailing edge, as you see, like the tail of a comet or something extending off into the background. But I have one other night taken after the next night, and it's kind of the shape of the transfer is different, and the air bars on this is actually a V-flow plot and it has the air bars, and they're really pretty tiny. I was down to about 0.01, 0.015 here at 17th magnitude with 3-minute exposures. And so it's it's very interesting that I think that even the small dips, especially the ones that repeat on the different nights, are actually significant stuff that's in orbit around the white dwarf at this distance. So projects for the future, I got interested in this because it was a relatively faint target and a more challenging one, and thought, well, this would be cool. I had a student that was interested in working on this object as well, and so kind of jumped at the chance to telescope tuned up here this spring. But that's what I have on this. Thank you very much.
Thank you, Mike. Very interesting talk. Any questions?
How bright can you go with that system, Mike? How bright a star can you observe? The field you said is 26 degrees on the side?
With the kill, how bright they do targets down to 5 or 6 magnitude. I think because they're taking a little bit longer exposures than the bright star monitors generally. So they're not as interested in the really bright, Betelgeuse or something like that monitoring. But
could they go to bright second and third magnitude stars?
They could, yes. They'd have to do it special from their observing routine, though.
Other questions?
They go down most of the targets come out to be 9, 10, 11 magnitude. Occasionally there's a 12th magnitude, but not really beyond that much.
Just to comment on your white dwarf light curve, Mario and we've been doing some observing, and we got results not unlike that.
Well, that's good to hear. I'd like to hear that.
Are they in the database?
They went to Mario and
Mario was collaborating with someone at MIT.
Yeah,
I don't know if your data went to MIT or not.
Yeah, and the night of data from New Mexico, the night of data from New Mexico that our student had, the transits were kind of different take from this. I know they did shorter exposures than I was comfortable with. They wanted more time resolution, and it's a balancing act when you have something happening quickly, especially if it's faint. And so I remember the old days of multiplier photometry. Talk about going to school in the dark ages. Looking at a star like a 13th magnitude star with a 24-inch telescope like BL-CAM that pulsates every 56 minutes, and you're always starved for photons, trying to get a light curve on that. More?
Since the star is in Cygnus, I wondered if it would have been observed by the Kepler spacecraft. Would it be in the field of view?
I believe this one is just outside of the Kepler field.
Okay, thanks.
It's more toward the opposite side from Lyra, from the Cygnus.
And I missed what magnitude it was.
It's about 12. The Sinbad magnitude is like 11.99 or something.
More questions? Well, if there are no more questions, let's thank Mike again, and thank you very much.